Welcome to the second video on the distributed ML training with PyTorch using itwinai. So as you can see, we have a new patch which is going to be released soon. So with respect to the next video, the current version of itwinai is now 0.2.2. And in this video, we're going to see how to use the TorchTrainer to train a simple neural network on the popular MNIST dataset. So let's see what are we going to do today with the TorchTrainer. So how do we use the TorchTrainer? To recap, the TorchTrainer is a Python class, is implemented as a Python class, and it provides an interface, a data interface to be used in an itwinai pipeline, on the one hand. But on the other hand, the goal of the itwinai TorchTrainer is to simplify the access to advanced machine learning tools to scientists that don't have the time, don't have the interest in learning how to use all of these functionalities. So we're doing it for you so that you can access distributed machine learning, rich machine learning logging, and so on and so forth. So the TorchTrainer executes a method, which is the execute method, which receives three arguments: the training, validation, and test dataset. It returns a tuple of 4 elements. So the first 3 elements of the return tuple are the same as the inputs, so train, validation, and test, so they are propagated, plus the trained machine learning model. This is at runtime when we execute a trainer. But when a trainer is instantiated, well, we will need to provide additional information. So first of all, the neural network to be trained for the trainer. So a single neural network model, Torch neural network, a distributed machine learning strategy, which will be applied when the resources are available. So if you're running the TorchTrainer, even if you're giving a strategy, let's say if you're giving a deep speed distributed strategy, but you only have one GPU, the trainer will adapt automatically, telling you that it would really like to run distributed ML, but it cannot because it only has one GPU. So it will fall back to non-distributed strategy. But when the resources are available, so multiple GPUs, multiple compute nodes, the trainer will automatically make sure that your training is distributed. Probably the most important item is the training configuration in Violet. So the training configuration is an object that contains all the hyperparameters and user-specific configuration that will be used during training. We are also passing a logger, so like MLflow, TensorBoard, weights and biases logger, a list of them, so we can also log using multiple loggers, and a list of machine learning metrics. Among all of these items that I just presented, the only mandatory ones to to utilize the trainer are the machine learning model to train, of course. So we need something to train, a training configuration, and that's it. Then, if you want, you can specify which distributed ML strategy to use, whether or not to use a logger, and which one. And if you want, you can specify some metrics that will be used to assess your model while training. So, as usual, let's go and see how to find all of this information in the itwinai documentation page. So if we go under Python API reference, and again, itwinai PyTorch modules, we will look for the trainer. So the trainer is the actual Python class that is implementing the logic I just described. So as you can see, these are the constructor arguments, and I would like to spend some time on the configuration. So the training configuration is an object. Can either be a dictionary, Python dictionary, or a training configuration object. So if we jump into training configuration, we will see that it already provides. This is like a Python data class. Is a Pydantic model, but it's like a data class, and it already provides some common configuration items, such as the batch size, whether to shuffle the dataset, the name of the optimizer to use, learning rate, momentum, weight decay, and so on and so forth. But this configuration object supports also custom fields, so you can add all the fields that you want. And all of these fields already provide a default value. So for the batch size, the default would be 32, but you can change this, of course. And let's go back to the trainer. So as I said, we also support a logger. So the logger, let's jump to the loggers. Here is the list of all the loggers you can use. So console logger, MLflow logger, weights and biases, TensorBoard, and a collection of logos of the previous ones. So now, without further ado, let's move to the code and let's do some coding. So let's move to here. So to start with, actually, let's start from a simple example. So we will be using the MNIST training. We will be adapting the MNIST example provided by PyTorch. So well, let's start by copying the network and the imports, and yes. So very well. So we start by creating a neural network. So in this case, I don't. In this case, what is our neural network doing? So it's creating some convolutional layers, some dropout, and is applying them for convolution, ReLU activation function, and so on and so forth. So I don't want to return the log softmax, but I want to return the logits, just because I prefer it like this. So we will not apply any activation on the last layer, and so very good. So of course, yeah, some imports are not used yet, but let's go on. Let's continue. So we're going to ignore the train and test functions because this logic is already provided by the TorchTrainer. So let's go on. Let's copy the main, and let's copy the main. The first part of the main. So we start by creating a main function, a main. Okay, then we don't care about these. We want our code to be simple. So yeah, actually I have it pre-cooked, so I will just paste the simplified version of this. We want less arguments, and then yes, and then let's see here this use CUDA, use MPS. This is all of these. Also the random seed is managed by the under the hood by the itwinai TorchTrainer, so we don't need to have this in our code. Here what they're doing is setting up the constructor arguments for the data loaders. But again, this will be managed by the TorchTrainer, as we will see shortly. So let's just focus on the datasets. So we will use here. So let's create the datasets. So first of all, so we will use the MNIST dataset from PyTorch, from Torch Vision actually. So very easy, just import the MNIST dataset like this, specify where we want to save the data. Let's save the data in a local folder called data. So, and now what I'm going to do is rename them, and okay. Now it's a bit more understandable. So as you can see, when you give the flag train equals to true, we will have the train dataset. Very good. Okay, now we have the datasets, and also with the transforms, so with some preprocessing already done. Let's create our neural network. Let's instantiate our neural network. So it's called net. Very creative name. So now we can start by using, so we have everything that we need. So we have a neural network to train, we have a train validation dataset. So let's get started, and let's start playing around with itwinai. So we will not use a learning rate failure. We don't need that. We also don't need the optimizer. We will let the trainer do everything for us. So first of all, from torch trainer, and then let's start by creating a trainer. Equals TorchTrainer, and so the first thing that we need to pass to the trainer is the configuration. So a training configuration. So let's do this. So from itwinai torch training configuration. Very good. So now training config equals on we spell error. Now let's go. So what do we want to pass? Well, that size, we receive it from the arguments from command line. So this is the first item, that size. So let's
let's override the default value with the ones part from the command line. So we do args.size. Then another argument is well, the strategy, but the learning rate. So let's also, before giving the learning rate, let's also give an optimizer. So optimizer. So let's go back to the example. So what optimizer were they using in the tutorial? They were using ADA delta. Okay, so let's use ADA delta. Okay, and then we give a learning rate. Optimizer learning rate equals to add learning rate. Let's save, and we can see that now we're passing the learning rate, which is an hyperparameter, where we're setting it in the torch configuration, and in the training configuration. And then another thing that we want to set in the training configuration, so we set the batch size, we set the optimizer. The last thing that we need to set is the loss function. So loss equals to, so what loss were they using? Let's see. They were using the negative log likelihood loss, but since we are not, since I changed the output of the neural network, now the network is returning the logits, I'm going to use the cross entropy loss. So loss equals to cross entropy. Already there. Good. Very good. So now we have everything that we needed in the training configuration. So let's start to populate the trainers. Config equals training configuration, the object that we just created. Now we pass a model equals to net. Very good. Okay. So yeah, let's start like this. So let's start simple. We have everything that we need: a model to train, a configuration, and a trainer. The last step, of course, is to run the training. So we're trainer.execute. Okay, so we execute the trainer, and when executing the trainer, we pass the dataset. So train dataset, validation dataset, and we pass none for the test dataset because we don't have it and we don't care. It's totally fine. So let's save. Another thing actually that we can set is the number of epochs. So for how many epochs do we want to train? Let's give it to them. So epochs equals args.epochs. Let's see. Seed, of course. But let's also set a random seed for reproducibility. So the TorchTrainer will set a random seed before starting the training. This way, it will make sure that the different experiments are reproducible. We could also set the distributed strategy, but I mean, we're not running a distributed job now, so we can safely skip this, and we will. So for the moment, let's just run on the. Let's just use this setup. So Python train the 5. So as we can see, first the script downloaded the dataset, which was done at this point. So the Torch Vision dataset automatically downloaded the MNIST dataset, which only needs to be done once. And then the trainer, then we get a message that the Torch Trainer is being executed. So this, and then now the output is very poor because we don't get any output, any information about loss, any other thing. We just know that some checkpointing is being done. Of course, we can also change how often the model is checkpointing, like we can and it will save a checkpoint every 10 epochs. Checkpoint area. But let's not worry about this at the moment. So a new checkpoint is saved as a best model every time that the validation loss improves. So okay, so now as we can see, the Torch Trainer is finished. As I said, there isn't much. So if we look at the current directory, we see that we have 3 folders. Okay, data, which is where the data was stored, and then logs, and checkpoints. So checkpoints is the folder containing the best models and pretty much it. So now let's add some information. So as I said, we would like to know more. So let's add a logger. So logger, let's import it before. So from logger, logger. Let's use MLflow. Let's use MLflow. So create a logger, and then we create an experiment with the name amist tutorial. Then log frequency type. Log frequency is an important parameter in the itwinai loggers, and by default it defaults to epoch, which means you will log only at the end of an epoch, or anyways you will log once per epoch. But if we set batch, we will log a matrix for each batch, so the matrix computed on each batch. And if we give a number like 10, we will log every 10 batches. Now that we created the logger, let's pass it to the trainer. So logger equals logger. And there we go. So let's run this again. Very good. So again, the training is finished successfully in a bit more than a minute. So again, we didn't get many logs here because we are not using the console logger. The console logger will print the logs here, but we're using the MLflow logger. So let's visualize the logs in the browser, in the web browser. So to do that, we will use this command itwinai MLflow UI. Then we will give a path where the logs live, which is inside by default. If you don't change this, they will be inside ML logs, MLflow. So this command will spawn an MLflow UI. So let's open this in the browser. And here, under the amist tutorial experiment that we just created, we will find new run. So here we have the TorchTrainer is already saving for us the hyperparameters, which are basically the torch configuration, the object that we used before. So yeah, for instance, we're using ADA delta optimizer. By default is using the learning rate of 1. We have some metrics here. So we have the validation, training validation. So let's visualize the metrics. So as you can see here, we can already visualize the evolution of some metrics using MLflow. And to do that, well, we can just visualize. Later we can see them one by one. We have two variants for each metric. We have the train loss and the train loss epoch. The train loss is logged every 10 batches, but it could be logged for every batch, so the loss computed on each batch. Whereas the train loss epoch is the average of train loss across one epoch. So since we trained for, let's see for how many epochs we trained. So the default number is 14, so we trained for 14 epochs. This means that here we have 14 data points. The validation loss, and this is the evolution of the validation loss over the epochs. Okay, very well. So here we already have some hyperparameters stored in the MLflow logger, some metrics. We also have some system metrics now. We also have an artifact, which is the best model. So the model weights of the best neural network. And what is the best neural network? Is a snapshot of the weights of the model that got to the lowest validation loss. So a model probably that was saved with the head around here when the validation loss was the lowest. Now, as I said at the beginning of the video, we can enrich this logging even more. So we can add the metrics. So let's add some metrics. The metrics are imported, are reused from Torch metrics. So import Torch metrics. And so we don't want to redefine accuracies. This is a classification problem, right? So we don't want to write the accuracy metrics, the precision and recall. We want to reuse them. So let's reuse them. Metrics. So metrics are a dictionary. and then we will call them Q, and then we will do torch method of accuracy, and then we need to specify for what task we're computing the accuracy. So task needs to be multi-class, and then we need to specify the number of classes. So mnif is a data set of digits, so we have 10 classes. And similarly, we can also create a new metric, which we call, for instance, precision. And then we use the torch metric precision. And here we go. We have yet another metric. We could add as many metrics as we want. We could also add custom metrics. We don't need to. We're not forced to use torch metrics. It's just that torch metrics is already providing this to us. But if you want, you can add a metric of your a custom metric of your choice here. You're totally free to do that. And then we add the metrics. Metrics equal metrics. Very good. So now let's run the training once again. But this time we want to have more metrics to study the evolution of the training of our neural network. Very good. So the trainer has finished once more. As we can see, it took a bit more time because now it's logging more values. So the more we log, the slower it will be. But now let's visualize the results. So let's go back to our experiment and this tutorial. And let's see the new metrics. So as we can see, we have we not only have the loss, but we also have the precision and the accuracy. So this is the validation accuracy per epoch. This is the validation precision per epoch. So as you can see, we're getting very. Let's see. Okay, now let's visualize metrics a bit better. So let's visualize the validation accuracy per epoch. So validation accuracy epoch. How the validation accuracy evolves. So that's the steps. So as you can see, we reach almost the 99%. We reach the 99%, almost 100% accuracy. But in classification problems, when the dataset is imbalanced, maybe, or we also want to check the precision and recall. So let's check also the validation precision, precision epoch. Again, we get a really high value here as well. So we will check. We can also add the recall and other metrics supported by torch metrics. So here now we can stop the MFlow UI. We don't need it anymore. So basically, to summarize what we saw today, we saw that it's possible to train a generic neural network, any kind of neural network, using the itwinai TorchTrainer, which can be used directly inside a Python script, and it receives a training configuration with all the hyperparameters. You can also give the custom values like my param equals 43. You can also do it like this, and then in the TorchTrainer, you will override the TorchTrainer, and you will change the portion of code that needs to be aware of this parameter. We saw how to use the logger, so you can use additional loggers if you want, how to use metrics, and in a very short and simple script, we were able to access all of these functionalities. The TorchTrainer, of course, allows also for distributed machine learning. So if we add a strategy, if you like, in the strategy argument, we can specify which distributed strategy to use. For now, I will just use the one selected and provided from the command line on the strategy, args.strategy. And we will see now how to run distributed machine learning using the TorchTrainer. Very well, so now let's continue training, and this time we're going to run distributed machine learning training. So we still have the script, so I just allocated some resources on Unix supercomputer, so let's see. We have 4 video GPUs for Tesla V100 available, so a full node is allocated to this job now. So as a next step, I'm going to use a command to launch the distributed training. And to do that, I'm going to use torchrun. So torchrun is a command provided by Torch, plus flex, like the number of nodes, in this case only one, the number of processes per node will be equal to 4 of GPU, which is the number of GPUs, and then finally train.py, which is our script, and we pass the strategy. So the strategy flag has to be consistent with the distributed strategy launcher that we use. So when we use torch data parallel, so DDP, we need to use torch. So let's launch the distributed machine learning training, and again I will speed up this. So while training, I've noticed that on the terminal I'm getting so many warnings here from the data loader, saying that basically the number of workers I'm using is too much. So now we're trying to set to use 4 number of workers, which is the default value in the training configuration. So number of workers data loader is 4, but apparently the resources that are allocated are not enough to support 16 workers, 4 workers for each data loader, for each distributed worker. So I'm going to kill the job and change this. So let's change it. So worker data loader, let's put it to 1, and let's run the training again. Very well, so now as we can see, we got rid of the warnings, and again, of course, we have the messages telling us that the test models were saved. As you can see, the time that the TorchTrainer took is huge, but this is of course expected because we're running distributed training on a very small model, for a very small model on a very small dataset. So the communication overhead between the workers and the overhead of setting up the communication backend are so large, so big, that basically it's not worth it to run distributed ML. But we are not here to improve to run distributed ML to improve training performance, but just to learn how to do that, so that when we'll be using larger models and larger datasets, distributed ML will actually improve the training time. So thanks for following this tutorial, and see you in the next video.